Hi, take a look at this. Magnetic north, magnetic north, and magnetic south. All right, do you see that? Magnetic north and magnetic south, right in the middle. All right. Let me move this and see what's beneath here, right? Ooh, look at that. These are the same, basically. Yeah, what's beneath here is different. You see? Now, what's beneath these? Oh, let me show you. These are really strong magnets. Neodymium. I think they're like N50 or something. It's just crazy strong. Alright, you see? I have the black parts over here. Alright, north, north, north. So, the magnet doesn't want to be in the center in this one, and it goes right near the edge, right? Now this one, it can be placed on the center, but it jumps between here and here. And what you couldn't see when I had this on top of here, I don't know if you could see, but I could see already. You see like a fine two circles, the brighter circles. Yeah, you see it right now, yeah? So the inner space between the two magnets, the black part between the two lighter circles, that's magnetic south between the two magnetic north facing magnets, right? And this goes to show that the ring magnet is facing north, north side up, and the inner black magnet, black flat cylinder magnet on the right, is facing south up towards the camera. And take a look at this. Alright? These black ones are like this. Now, what happens if I put magnetic north up, side up in this magnet? Remember that it has this geometry. Although at a distance you cannot tell, but when you get close, it starts with a dot and then it starts with then ends with a circle. Right? You see that? Now these are attracting right now. And voila. Remember The bottom one is magnetic north side up, the ring magnet, and the cylinder magnet. And it's gone. The center magnetic magnetic south pole up disappears. What I'm doing is like putting another one on top, but like not touching it, not quite going on top of itself. Alright. So this one, at a certain distance, it's homogeneously uniform magnetic north side up, but if you go closer, it's not homogeneous north side up. It's heterogeneous magnetic field, or more than one magnetic field. But this is using two different masses, or two different objects that's not connected to each other physically, but they're connected to each other magnetically, so to speak. Alright. Now, putting this on top of it, just gonna go slightly closer. And the center part, the center circle, is bigger. As it descends and touches the bottom two magnets, the top magnet becomes influenced by the stronger bottom magnets, and it gets overpowered, just as this one gets overpowered, and has the center magnetic south facing towards the camera vanish under the influence of the magnetic north side up ring magnet and cylinder magnet. So to demonstrate, it's kind of hard to do it again. See, and as it gets influenced by the field, the color changes, and the bright spot disappears, and becomes one with the magnet, so to speak, or overpowered by the magnetic field beneath it of the bottom three magnets. Since there's this one. Alright. Now, what was the point of this? Well, the point of this video is more about showing you that magnet is not really as simple as you think it is, since something that is set up like this, it generally still likes to be at the edge of the magnet, this smaller magnetic pole finder magnet to this magnet. It likes the edge more, If you believe it or not, I don't care. It's much stronger at the edge. The acceleration towards the magnet as one whole system, sharing each other's magnetic field. It's still stronger here, even though it kind of wants to be in the center too. If you place it in the center, it's also off-centered at the same time. If I could put it at the center, it kind of doesn't like the center, and it doesn't want to be over here because that's the faint magnetic south side going against the magnetic south side of the smaller magnet that I'm using to find the poles of the magnet. And this one, you could really see how that it doesn't like the center. Yet at the same time, from a distance, the magnet is the same. It shares the same field at this distance at least. And closer it gets, it separates. So the magnetic north, south, and north and south, right? This whole area over here is showing the opposite polarity to this. So this polarity is the same as this. If you don't know which side is magnetic north or magnetic south, at least you could intuit that from using the magnetic viewing film, which is why I still use it, because it's simple to use. Alright? And here's my hypothesis that how I even got this magnet, it's not because it was originally like this. It was really more originally like this these two magnets like this, but with this at a distance like here. But it gets depolarized at the center. It gets depolarized at the center. So, but in depolarizing the center, it leaves a opposite magnetic field movement to the edge current, as someone would say, of the loop of electrical spin of the neodymium iron boron, of the atoms aligning at a distance in synchronicity at a certain percentage of the atoms with itself sharing the same magnetic field. Alright? However, what makes this different than this, I couldn't get it off. Couldn't get it off camera because it's really hard to do it on the table. So what makes this different from this is that this is essentially one magnet using one connected field, mass held together. But this is two masses together, which is why this is not quite the same as this, because this has 2 point sources. I mean, 2 places, 2 objects, and 2 magnetic fields that are sharing the same center. But this, however, is just itself. So what I'm trying to get to is that a magnet gets polarized like this, alright, as like this one at a distance, ignoring the center 2 circles, right? It starts off like this. I didn't get it like this. I placed it in the field like this one, so that the outer magnetic field remains the same, but the inner magnetic field flips, so to speak. So what was in this one, since the original magnet was this, basically the field, I think the center part is depolarized, so it doesn't really have its own magnetic field. However, the depolarized area leaves off area that is still polarized, magnetically polarized, but in relation to the mass of the outer edge to the depolarized inner mass, it's as if the mass doesn't exist for the magnet somewhat. So in essence, it's basically same as a ring magnet without the center part, cylinder magnet as I have here. It's more like a standalone ring magnet, but with the incoherent mass in the center, with coherent mass on the edge. And why is that important? Well, I'll get to that later. I'm doing stuff behind the scenes right now. So you guys don't really see much of the side view of the magnets. Oof, wait, fixing the camera settings. Lots of stuff happening in the background. So what I'm thinking is that this, if you split it in the center, you only get the polarized parts of the magnet to show. So the center part, you will not see a strike line, inertia plane, so to speak, but rather a void, an actual magnetic void, because there's actually no magnetic field there, so to speak. but it's in the outer edge, which means there's depth of field, so to speak. It's kind of hard to do with something like this, but just imagine that this part right here, where it dips, that's where that's basically the equivalent of slicing this right there, where it dips. And I don't have a broken disc magnet, this kind of disc magnet with this polarity magnetic field, but I will say that what I'm saying here is true, that it really does have like a dip like that, and it is not polarized at the center. The center is the most easiest place to depolarize, while the edge is the hardest place to depolarize. It begins at the center, and that's the interesting part, because where there's no magnetism is at the center of the magnet in a strange sense. That is at least what nature tries to accomplish. So this time I have 3 magnets over here. This looks like that, and you see that? That's what it should look like if your magnet, if you're a ring magnet, and the center of the magnet was in opposite polarity, or just a magnet, not just a ring magnet itself, kind of looks like that, only at the top view, assuming this part is the same. And this is just an analog for like a section of the ring magnet or the disc magnet. Okay, so what I'm saying here is that you will not get this field to a section of this. If you cut it right between the center part, you will not get this side view of this magnet. You will not get this. Instead, the center part is gone and it's around it. Okay? And my reason for that is because, again, the center part is depolarizing first. Then the magnetic edge gets depolarized. It begins at the center and spreads outwards. The mechanism for decohering of coherent magnetic field. And the challenge is you prove it, because I already proven it by myself, and I have videos existing that has shown the side view of the magnet, of the broken magnet of the same disc magnet with this is just an epoxy coating of a neodymium iron boron magnet. Okay, so the reason why there's a magnetic field in the center is oddly because there's no magnetic field in the center, but rather the magnetic field around it going one way goes another way when there is no magnetic field at the center. So geometry of the magnetic field tied to the mass is important and shouldn't be neglected. And air is basically functioning like a incoherent mass, although it kind of aligns to the magnetic field at a distance. Might seem the same, but at close it doesn't exist, but it is influenced by the magnetic field to have a fake resemblance of a magnetic field at the center. And I could show it like this. At a certain distance, you could see it right there. You see that? Opposite to each other. Yet, again, at the center, it's not there, right? There is no bright line in the center, but there is a more spread out like magnetic field with the depth of field like that at this angle. Assuming this is like half a ring magnet, okay? So just adding one more for a better effect. So you will get that, right? You will not get, however, I'm gonna flip the middle one. You will not get this. You will not get this when you cut this in half. Did I get through your minds? Alright. That is why experimentation is important, because in theory you would think that this is the same as this, when in actuality is there's a distinction with a difference, even though from the top it basically looks the same as half a ring magnet, half of the disk magnet, or the ring magnet really, because the air core, so to speak, is the same as the incoherent part of the neodymium iron boron of the disk magnet. Did I get the point through? I hope so. Goodbye.